Soren Oyer, following station at the universities of Dresden, Ekaterinburg, Leipzig, Pennsylvania, Bonn, and the Fraunhofer Society, Soren was appointed professor of data science and digital libraries at Leibniz Universität Hannover and director of the TIB in 2017. Soren has made important contributions to semantic technologies, knowledge engineering, and information systems. He is the author of over 100 peer-reviewed scientific publications. He has received several awards, including an ERC Consolidator grant from the European Research Council, a SWSA 10-year award, the ESWC 7-year Best Paper Award, and the OpenCourseware Innovation Award. So welcome and thank you for joining, Soren. Let's take it away.
Wonderful. So thank you very much for inviting us to this event. It's really great. And I will talk today a bit about the Open Research Knowledge Graph, which we are working on. And our idea is also to map science, but probably from a different angle than what others of you or of this community are doing. So we want to actually look deep into scientific contributions and organize these scientific contributions and provide some better overview on scientific insights with the Open Research Knowledge Graph. But before I tell you a bit more about the Open Research Knowledge Graph, let me maybe start with discussing a bit what different how information flows changed in the digital era in different domains. Yeah, so for example, there were mail order catalogs. In Germany, Quelle-Katalog, which you see on the left, was extremely popular. Maybe also one of the reasons why the Iron Wall was falling between East and West Germany, because East Germans want to have access to these cool products which were described and printed in this mail order catalogs, which were hugely popular in the 80s, 90s, 2000s, and completely disappeared nowadays. And similarly, street maps, which you needed to buy every year if you went on holiday, wanted to go somewhere, you needed to buy a map. There was a whole industry of publishing houses around publishing these kind of maps and update them every year. Phone books, encyclopedias, you name it, there are many of these examples. And how did it change? We use now digital services. So we use, for example, eBay or Amazon or Idealo for e-commerce. We use Google Maps or OpenStreetMaps or navigation systems for navigation. We use Wikipedia as an encyclopedia, and so on and so forth. And these are not just pseudo-digitized copies of the analog versions. So we don't use a PDF scan of a mail order catalog or a PDF scan of a street map, which is sent to us by email, but these are really digital-born services where we also the paradigms, underlying paradigms profoundly changed. So we have new means adapted to these new possibilities, like we can zoom into the data, we have much more dynamics, the business models changed completely, whole industries got disrupted, there is much more focus on data, on the interlinking of data, on services search in the data, also on crowdsourcing, data curation. And now, how does it look in science and in scholarly communication? Yeah, and if we look how scholarly communication has changed over the hundreds of years, it actually didn't change much. Yeah, the typography changed a bit. Of course, we can now access these publications as PDF articles over the internet much faster. We don't need printing and mailing of books and journals. But this would be the same as sending a mail order catalog by email, a PDF scan of a mail order catalog or a PDF scan of a street map. And who would use that nowadays? And the question is, why don't we have more adequate services for organizing scholarly communication, research insights in a digital way, and beyond these traditional unstructured static papers which we are used to write. Also, we have a number of problems in science, the digitalization of science, data integration, analysis, digital collaboration is a challenge. We have also monopolization by commercial actors like publishers, which exploit lock-in effects and aim at maximizing profits. We have reproducibility crisis. So many experiments are hard or not reproducible. And that's one of the pillars of science, reproducibility. We have this proliferation of publications. So the publication output doubled within a decade, and it continues to rise. And you can imagine with this flood of publications, basically, we have a deficiency of peer review. The quality of peer reviewing is deteriorating. We have predatory publishing. So I would say some of the foundations of science are actually endangered, and science is at risk. I think there is a lot of duplication and inefficiency. But how can we avoid this if the terminology, the research problems, the approaches, methods, characteristics, evaluations are not properly defined and identified? They are described in this unstructured text. Every author describes it with his own words, using slightly different definitions and terms, and it's often actually a big mess. So if you compare this to other domains, how could you build an engine or a building without properly defining the parts or the relationships, the materials and the characteristics? And what we want to do in science is actually build a house of wisdom, a house of knowledge, of scholarly knowledge, right? So these different parts, relationships, they need to fit together. My impression is they currently don't fit very well. In most cases, of course, there are some exemptions. So what we have a lack of transparency. Often information is hidden in this text. And of course, papers are also written for getting through peer review. So not all the aspects are described in the same unbiased, balanced way, but sometimes, of course, authors are trained to present their work from the best and most positive angle. Then we have a lack of integratability. So we can actually not easily fit different research results together. It's very cumbersome. We also have a lack of machine assistance. This unstructured content, basically these piles of PDF articles, they are extremely hard to process. I would say not only hard, almost impossible to process. So we cannot really do question answering and more advanced assistance, for example, on these papers. What we can do is a bit identifying, recommending maybe articles, or supporting the serendipity effect by showing you some connections, but really juxtaposing different research results and showing the advantages and disadvantages in a comparative manner, or answering questions. That's something which cannot be done currently, and the root cause is really this unstructured representation of scholarly communication. We have also a lack of identifiability. So metadata, of course, we are working on. We now have DOIs for identifying the documents. We have ORCIDs for identifying the authors, ORs for organizations. But metadata, I think, is maybe only secondary or not very relevant. Researchers are interested, what are the research approaches, the problems, the methods which are used, materials, the results, and these kind of things are currently not really identifiable. Collaboration, we have this one brain barrier. We cannot easily collaborate in larger groups And often scientists look for the needle in the haystack. And I want to illustrate that here with a screenshot, which is actually already more than 2 years, 2.5 years old. And the number of search results in these 2.5 years quadrupled. So I did this search just recently and found that when you search for this famous genome editing method, CRISPR, you actually find almost 1 million results. So 2.5 years, it was 238,000 results. And if you are then interested in how good is CRISPR with regard to precision, safety, and cost compared to other genome editing methods, what specifics has it when it's applied to insects, or who has applied it to butterflies, then you're really lost in this huge pile of publications. You have to either do years of research to answer these questions or to ask someone who has done these years of research. And that really prevents interdisciplinarity. It prevents also young researchers to get acquainted and get productive in science if we cannot organize this scholarly knowledge in a better way. So this is a bit depressing, right? So how can we fix it? How can we improve this? And our vision is that we represent overarching concepts like research problems, definitions, research approaches, methods, also different artifacts which play a role in the research life cycle, in addition to publications, also data, software, image, audio, video, knowledge graphs. And then also domain-specific concepts, which are very specific in different research domains. Like in mathematics, you have definitions, theorems, proofs. In physics, experiments, data, models. In chemistry, substances, structures, reactions, and so on and so forth. And our idea is to represent all these entities in a knowledge graph and establish the links and relationships between them in a semantic way that we describe what's the connection. And here we also see a bit the connection to mapping science, because a knowledge graph is basically a map of science, yeah, and then a map of the scientific concepts, the relationships between them, the research problems, and that's what we aim for. So we want to build this knowledge graph based on the linked data principles and FAIR principles. FAIR stands for making data findable, accessible, interoperable, and reusable. And that's often applied to research data, but we think it also needs to be applied to publications, to the PDF documents, basically. And the linked data principles are a perfect foundation for doing so. And the linked data principles, which were coined by Tim Berners-Lee, who is also the inventor of the web, basically say that you should use your eyes to identify things in the data, that you make them dereferenceable, so you can look them up on the web. You can actually enter these URIs into the address bar of your web browser and then get information, that you return a description in a standardized format. On the document web, we have HTML. On this data web, it's RDF, like the resource description framework, which was developed already more than 2 decades ago by W3C, and is a great standard, or actually now a family of standards for semantic representation of knowledge, information, and data. And then, as we have links on the document web, we can also include links to related things on this data web, and link between different knowledge graphs or between different knowledge bases, databases. These are the linked data principles, which I think are a perfect tool for realizing this vision. And I want to maybe briefly, before I show you actually a demo of how this works, I want to show you the concept, the idea. So here, for example, we have one article, CRISPR genome editing, and one article, a practical guide to CRISPR genome editing in Lepidoptera. Lepidoptera are actually butterflies. So And this article here is published in an open access repository, and we actually envision that when you publish such an article, that you fill out some kind of a form where you not only add the bibliographic metadata like author, title, and so on, but also information on the research problem which you address, on the methods which you use, on what materials they are applied, where the experimental data is located. And by filling out such a form, you actually populate a part of a knowledge graph, which you see on the lower part of the slide. And then when we put many of these small descriptions together, we actually have a large knowledge graph, and we can then use, for example, question answering in order to answer certain questions. So an intuitive exploration which leverages this rich semantic representation allows us to answer natural language questions. For example, you could ask a question, how do different genome editing techniques compare? And then we can parse this question, detect named entities, also relationships. In the question, we can construct a query. There's a SPARQL query language for RDF knowledge bases. Execute a query on the knowledge graph and then render the results and show, for example, a tabular comparison to the user, which you can see here, how this could look like. And question answering, we are used to do this already. Many of you use, I guess, Amazon Alexa or Google Now, Apple Siri for asking questions. And this, of course, only works because there is some structured information, data, and knowledge behind. And that's exactly what we need to build such a knowledge base. And I want to show you how this actually can work in practice. And we develop this service. It's called Open Research Knowledge Graph, and it's exactly this facility which allows to realize such a structured representation of scholarly knowledge. So when you go to the webpage, it's orkg.org. And let me maybe switch to the full screen mode so you can see this better. So on the homepage, you can browse by research field, or you can here look at the top featured comparisons. And these comparisons of the state of the art are the core element in the Open Research Knowledge Graph. And let me maybe select here this COVID-19 reproductive number estimates. So this is a research question which is affecting our lives now almost for 2 years already. And the question is, how does the COVID-19 virus reproduce, or how many people get infected by one infected person? So this R0 value, which also determines how many people have to get vaccinated or cured, and which also changes with different variants. So we had the original wild type variant, and then we had the Delta variant, for example. Now the Omicron one is on the horizon. So in each of these variants has different characteristics in this reproductive number estimates, and then of course also an impact on the life of people. And we analyzed studies which try to answer this research question. What's the reproductive number estimate for COVID-19? So this was a research question for the original variant of the virus, which was tackled like more than 1 year ago. And we found 31 of these studies, which you can see here on top. We added these studies to this Open Research Knowledge Graph. And you can see here in this table, each of the study is basically in one of the columns. Yeah, and you can scroll to the right, and you can see there are 31 of these columns. For each study, basically one column. And then we have for the study a description of the most important facts for answering the research question. So basically what you want to know is, where was the study performed? So the first one here in Lombardy, Italy. When was it performed? And this one was done in January to March 2020. What is the basic reproduction number? So it's 3.1 here for the first study, 3.6 for the second, and so on. And then also the confidence interval. And then for some of the studies, we have the methods they applied and the approaches. So we basically added this information for the 31 studies to this knowledge graph. And as a result, we have it already in a more better overview. Yeah, you can now basically scroll through this table and you see it's mostly between 3 and 4. There are some outliers here where it's just 1 and 1.5 or 6, but mostly it's around 3 to 4, which was then also the answer for this research question about the wild type. And then since each of the studies is actually a PDF document having 10, 20 pages, and it's very, if you imagine you have to read like 31 of these studies, each one 10, 15, 20 pages. So basically to answer this question of what's the reproductive number estimate for COVID-19, you have to read hundreds of pages. Here you now have it in a table which gives you an overview, but of course even this table is still not maybe the best way, but you can actually also create visualizations, since we have it not just in a table, but we have it in a structured representation in our knowledge graph. We can now also visualize this information in a table, and we see here, for example, a visualization of these R0 values and confidence intervals in this column chart. And we now have on the x-axis the contributions, so we can actually change that and for example, have the location there. So we can then create different types of visualizations based on this information from the Open Research Knowledge Graph, because it's a semantic representation. Let's maybe look at one particular study. So if we click on one of these studies, we have the bibliographic metadata here on top, which you can see. And then we have the contributions from this particular study here in this RDF representation. So subject, predicate, object. Subject is the contribution, predicate is the basic reproduction number, object is 3.1. And we can also look at the graph view. That's how the graph looks like. So we have the meta information. Actually, the metadata is not so interesting. More interesting is the contribution, and you can then actually click here and expand the contribution, and there you see the basic reproduction number, and there we can also see the 3.1 once it's expanded, and the confidence interval. Yeah? So you see here a graph of scientific contributions, and scientific knowledge is emerging. So let me close maybe this graph view. And what we also can do is we can actually edit the information. So once we signed in, we can then click on the edit button. And you see that this table here, or the structured representation, converts into a form. And I can click, for example, on adding a property. I can type something. And while I'm typing, it actually suggests me existing properties which we have already in the knowledge graph. So either I can create a new property, or I can choose an existing one. So let's choose here an existing one, and then the same works with the value. So I can start typing, and while I'm typing, it finds entities in the knowledge graphs, and I can reuse them and select them. So for example, I could here use Hanover, and then basically this would be linked to Hanover. Doesn't make sense here in that case, that's why I'm deleting it. Just wanted to show you that actually the idea is that the knowledge graph is created also in a crowdsourcing manner. We also want to, automatizing things. So Salomon in a few minutes will tell you how some extraction or knowledge generation can be automatized, but we also want to do a manual review of this automatically extracted information and crowdsourcing and curation of it. So on the right-hand side here, you can see the provenance, actually, where the information came from, who added it, and you can also see a timeline, who added what at what point in time. It's a bit like a wiki, so you can actually also then compare different revisions and collaborate on this structured comparisons. So, and you can also see that this is organized here. We see this research, this paper, which belongs to the research question of answering the COVID-19 reproductive number estimate, belongs to life sciences, to microbiology, and to virology. Okay, so I'm very sorry then you didn't see many of the things which I was talking about here, but maybe just briefly again. So here we have the homepage, we have these comparisons, and then these are 0 estimates. If you click here, you have a tabular overview of the basically, the studies and the contributions from these studies, and you can click on one of the studies, you get this representation there. When you click on edit, you can actually edit it, what I explained, add new properties, and then also add values here. That's what I tried to show. Okay. And you can, like the graph view, basically looks like that here. So, and then you can expand the nodes in the graph. Like, for example, the contribution is actually more interesting here. Yeah, we have to move this to the right. And then you can zoom into the graph and get more information about, for example, here, this basic reproduction number. So, and it's organized in this taxonomy here on top of research fields, and we can go to virology, and then you see an overview of the research field, of the contributors, of the different research problems which are tackled there, and then these different comparisons, for example, which for comparing the state of the art for certain research questions in this research field. Yeah, and that doesn't work only for life sciences, but here, for example, we have lots of examples on the homepage from different fields of science. So there's one where we have the greenhouse gas reductions, different scenarios for Germany. So there are 25 studies which you can see here on top. And these studies then give some information about how the greenhouse gases can be reduced, and it tackles different energy sources, and there are different scenarios, what reduction can be achieved till what time, and lots of structured information about these studies here organized in a table. And then, since we have the semantic representation, you can actually create a nice overview. Also different visualizations here, but you can see here about the installed capacity, for example, of renewable energy and other things. So to get an overview of the state of the art in a certain research field. Yeah, so we are, of course, still in the beginning. So if you go to statistics, we have like 500, almost 600 of these comparisons with almost 8,000 papers and 4,000 research problems, 11,000 contributions in 1,200 research fields. This sounds, of course, not bad for the start, but of course, we are also still far away from having science comprehensively covered, because there are millions of publications published every year. So there is a lot to do ahead of us. So on the one hand, we want to improve this crowdsourcing. On the other hand, we want to facilitate also the automatic extraction and interaction and integration of tools which automatize that, because It will not be possible to do this fully automatic. We always need human intelligence also involved, the intelligence of the crowd. We are now also working on integrating that into peer review processes of journals and conferences. But at the same time, of course, we also want to automatize as much as possible to support authors in creating these automatic in leveraging machine intelligence, basically, to create such representations in an automated way. And that nicely leads over to the next part of this presentation, which will be given by Salomon. So maybe we can switch over to Salomon now. Medina, can you hand over to? I stopped the sharing.
Panelist. He's already panelist. Yeah, he can share now.
Great.
Okay, yeah, hi everyone. So now I have the sharing option. Let me.
Yeah, we see your first slide, full screen.
Okay, can you see me as well?
Yes, I can see you.
Perfect. So yeah, I'm going to talk a little bit, continue where Zoran mentioned about the issue we're trying to address here with regard to interoperability and as well as trying to make machine assist our effort of trying to put knowledge that are available in PDF forms outside there in a more structural way with our platform, the Open Research Knowledge Graph. First, if you look at this picture, it may not seem like most of our office. I think this is a little bit scary, but if you think about it in an area where, in a time where maybe people didn't have computers and in past years where people were relying on these papers, having them printed, and with the amount of information that we have today accessible to us, you can think of an office looking like this. Maybe some of us, we have folders where we keep track of paper that we are currently reading and so on. And so you can see that more and more this trend is going on with the availability of also of the preprint paper that are available in PDF forms. And now our question is, how can we, in this era of scholarly exploding of information, how can we keep track with the rapid evolving research progress? So one of the idea that we are trying to go about is how can we use leaderboards, for people that are working machine learning and specifically natural language processing on all the empirical AI research. We try to track progress in this area with leaderboards where we can have some way of having all the researchers, all the research published, scored on a certain way, or it can be ordered that will help the community know where we are and in which direction we can move forward. So in this work, we're trying to use automatics tool using machine learning on how we can automatically giving a PDF. As I was starting with, we have a PDF as a starting point. How can we use a PDF, and from that PDF, we can automatically extract the information of task, dataset, and metric. So we are not going to just take all the automatic extracted information directly to our knowledge graph, but we are trying to use and we'll use the human in the loop approach in order to try to confirm if the information that has been extracted by our system is correct or not. So we leverage the natural language inference setup, and for this particular work that has been published, it was submitted at ICADL and is published at Springer. You can find it online, but we try to use now 3 transformer-based model, the Vanilla BERT, the SciBERT, and the XLNet, and use a natural language inference, or maybe elaborate more about the natural inference setup. So we have as input information, we have a ground truth information like task, dataset, metric, and we have something that is like a customized summarization of a full paper. So we have the content of the full paper that we extract with GrowBit. I will a little bit talk about it in the next slide. And with these 2 information, we are trying to learn a signal of knowing if a certain combination of leaderboard can be extracted or not from the given doc.tia. So, and I think one natural question that may arise now is, how do you get the ground truth task dataset metric information because we are doing in a supervised learning approach. So we need to have ground truth in order to train this system. Yes, we use some kind of distance supervision from paper with code knowledge base. This platform at daily basis update information in JSON form that contain this kind of information, and we try to use that in order to have signal to train our model. So let me go a little bit deeper on how we went about creating that data. So this is how if you go to the paper with code about or info, you will see this page. There's a couple of JSON files. So we focused on just on some of them to extract information that we wanted. We created a data set, and we use now GrowBit because now we have the signal, and now we have to download the paper. In order to get the content from the paper, we use GrowBit, and this is the overall statistic quickly of our paper. So we had around 753 papers for training. So this idea actually was this idea that we implemented was started by the IBM research in 2019, but they use a small subset of 170 papers. And as you can see, the statistic here, we have a very big leaderboard score. Like we have up to 1,000 leaderboards, 1,800 leaderboards option that we can try to categorize once we have a paper. Okay, so let me talk also about GrowBit, how we did that. So as I said, we take the knowledge from a paper with code, and the paper we download, we try to restrict it to the open access paper from arXiv specifically. So we just take the paper that's available on arXiv, we pass it to GrowBit, and we have the ground truth. For the training part, we pass the doc.tia. But what is doc.tia? So the doc.tia is an abbreviation for document, title, abstract, experimental setup, and table info. So what we are doing, we are taking the full content of title, the full content of the abstract, the full content of the experimental setup, and we are also taking some part of the table info. So for some of you that are familiar with BERT and SciBERT as well, we have a limitation of the number of tokens that we can give as an input to our model. So it's 512. So we have to find a way to, even though we had access to the full content of the paper, we want to get a way to summarize it to fit this requirement of these big models. So that's why we follow along this idea of using the doc.tia representation. Alongside with the ground truth from paper with code, we could now have a training data in order to start training our model. So actually the leaderboard triple look like this. In red, this is the task, this is the data set, and this is the metric. So this is the three information, the three triples. Great. So how does the data set look like? So now if you go to our, because the data is actually published, I will give you the link to the Zenodo repository that contains the data. You can look at it. So the data is actually looking something like this. So we have the TDM, which is the three tuples, and we have the paper context, which is the doc.tia, and you have the label here, we are using a natural language inference, so we had to give also negative signal to the model for the model to learn. For in this case, we have this paper 1312. This is a arXiv ID, which was addressing the task of image classification on the dataset CIFAR 100, and you can see that this paper was addressing two leaderboards here. We have minus and percentage error, but we give as well some negative instances. So those leaderboards are not present in this paper, but we give it to just help the model know what is present and what is not present in the paper. And I would like also to show that for the inference stage, so this is the right part, I've already discussed the left part. For this part, basically, after the system has been trained, for any paper that we can have, we can just feed it inside our system, and the paper will the system will automatically tell us what are the triples. So in which leaderboard can this paper belong to, and there's a certain probability that now the user can see on the screen or ORKG and decide to see which one can be approved or which one can be actually, it doesn't make sense from our system prediction. Great. So quickly, I will jump to the result. For the result here, we compare it with what was done in the literature, and our system is called the ORKG TDM. You can see here that on the same data set that Usman and all used in 2019, our XLNet TDM, ORKG TDM XLNet is actually outperforming the result with regard to macro precision and recall. You can see it on the slide. And we also use a special annotation for papers that have leaderboard that doesn't belong in our taxonomy. We are giving it an unknown label, and you can see also how the performance, what is the performance considering or excluding this unknown annotation. Great. We did also some ablation study on trying to see which part of DocTIA is most important. You can see from the left side here that we have just title and abstract, and the more entity we increase, obviously, the more also the system have enough context to extract information of interest. And on the right part, we created a new data set for this, a bigger data set for that matter, for experimenting, again, doing some benchmarking, and this has been released as well. So this is pretty high values. We cross-checked it before, we could not believe it, but it currently what the system can do in extracting task data set metric for a given paper. Great, so this is how the old pipeline it look like. We get data from paper with code, we filter it from data from archive, and we train our system, and we can use now the ORKG TDM leaderboard miner to be able to actually give a leaderboard automatically to a PDF of a research contribution. So this is really amazing, because before people were only focusing on abstract and conclusion, but in our case, we went ahead in going through the full paper and actually extracting directly from PDF the content and allowing a human in the loop approach in order to use it further in our system. So if you go to the orkg.org, you can see there is a benchmark option. When you saw the statistic, as Zoran was presenting the statistic page, there were also a benchmark option where we actually have all the benchmark that we have. For the moment, we manually loaded it, but we are in the process of implementing the system fully in the ORKG. So you can see the model name here. In our system, there's no score, so this is information that will be inputted by the user. But in the future, we're looking forward into including the score and some other new entities in the system. So this is actually what we are planning to do in the future, adding new entities like model names, GitHub link, and so on. But as well, we want to extend this same idea in other areas like material science or life science. We'll try to see how we can have the same concept and also to cross-check our implementation in this field. So yeah, that is something that we're going to do in the future. So thank you very much, and I think we look forward to your questions. Yeah.
Thank you, Salomon, for your great presentation. If you have any questions, please post it in the chat.
And I hope people could see the webinar link. So feel free to look in the webinar again for this demo parts, which were a bit scrambled here today. And if you have any questions, feel free to contact us, either me or Salomon. And we are eagerly looking for collaborators and people who want to work with us on the Open Research Node Graph. It's also completely open science, open source, open data infrastructure. So everyone is invited to join us there. Thank you.
Thank you very much for your presentations, both.